So today I'll be talking about some work I've done on grammar induction. The problem that I was interested in looking at, this is having to do with how we can learn a tractable representation for processing natural language in kind of an application scenario. More specifically, I think that the key word to focus is learning and tractability, and possibly natural language processing applications. The specific question I wanted to address breaks down into two parts. First, I wanted to find out how we should represent a grammar for processing, in this particular case, English. And the second problem was to say, how can we then learn the grammar automatically and efficiently in this particular representation. So to answer these questions, I will first begin by arguing for a representation that makes use of both probabilistic and lexical features. In particular, I will be working with a formalism called probabilistic lexicalized tree insertion grammar. I'll talk more about that later. And I have done some empirical studies showing that this formalism works well for two types of NLP tasks, whereas many formalisms tend to be developed and ran on a particular task, so that it doesn't quite generalize as well. I've also developed a learning algorithm based on the EM principle, expectation maximization principle, for PLTIG, and I'll show that we can do this very efficiently. And finally, I wanted to address a slightly different issue about the training process. I find that the real constraint isn't so much in improving, or it's not so much in the computational aspect, but rather in the amount of work that human has to perform in order to do the training process. So I wanted to look at a couple of issues to reduce the amount of work that human has to perform in building up the training data for the training, for the learning algorithm. And I will show that through this technique called sample selection, we can drastically reduce the amount of training data needed to learn grammar. So the first part of this is some background. I want to kind of just talk about what I think are interesting in constructing grammars and a particular grammar formalism, probabilistic lexicalized tree insertion grammar. So by grammar, in this case, I'm actually being fairly relaxed about it. I mean, anything that gives us a syntactic representation of the language, I would consider a grammar. So in this sense, a list of allowable sentences in the language can be kind of thought of as a very weak grammar. And then you can become more sophisticated and use more expressive power to get to finite state network, and then to context-free grammars, and possibly to a tree rewriting grammar, of which PLTIG is a type of. Once we have a grammar, we can perform various tasks such as error correction with the application in speech recognition, or context-dependent spelling correction, and also parsing, where we might want to be able to extract information or for machine translation purposes. There are many difficulties in constructing a grammar. I'll be mainly focused on these three. I think one of the major challenges is having to do with the ambiguity that exists in the language. I'm specifically looking at lexical ambiguity and also structural ambiguity, such as preposition attachment issues. A second component is the complexity of the language being big and having lots of exceptions to the rules compounds the ambiguity issues, and a lot of these exceptions to the rules are actually lexically dependent. And both of these factors, ambiguity and complexity, makes manually constructed grammars not really possible. We can do it for limited coverage, and we can do it for specific domain, but it's difficult to maintain as well.
Can you make an example of what you mean by lexical ambiguity?
So I was thinking something along the line of different senses for the same word, or even, if you want, different words that got acoustically sounded similar, something like that. So in order to meet these challenges, one way to do it is through probabilistic grammars. Probabilistic grammar attaches a probability to each of the grammar rules so that now we can compute the likelihood of a sentence in this language according to the grammar. With the probabilistic grammar, we can disambiguate by computing the likelihood of the sentence and use the global likelihood of the sentence to resolve local ambiguities within the sentence. In terms of complexity, we can use probability to capture more of the lexical aspect through the distribution over the words, which we will see more example of. And this parameterizing of the grammar allows us to forego manual construction of grammars and instead go through a more automated way of inducing grammar from a large corpus. So in a probabilistic grammar framework, we can recast the error correction problem as one of language modeling. So in this case, we were asking the question of how likely is it that sentence O is observed in the language as modeled by a grammar G. And then lexical disambiguation can be done in terms of picking the most likely observation given the grammar. So if we have a good grammar, then the first sentence should be more likely than the second. So a commonly used formalism for language modeling, often in speech recognition system, is the n-gram model, where it's essentially a finite state network with probabilities on the transition to the next state. And each state represents a history of n-1 words. This gives us a relation between words within a window of size n. But it doesn't give us any hierarchical structure, and it does not really deal with cases where the words are very far apart, expanding or that exceed the window of size n. And so we might want to increase the size to include a large enough window, but then we would have a lot of training data sparsity problem because we couldn't quite find enough data to fit all the parameters. So a second task that I was talking about was having to do with parsing. In a probabilistic framework, parsing can be seen as a problem of estimating the probability of a tree given the sentence and the grammar. And again, we would like to pick the tree with the highest probability. Assuming that we have a good grammar, then we might imagine that tree 1 would be much more likely than tree 2. And this will help us resolve any local ambiguities within the preposition attachment issue to get the globally more likely tree. So PCFGs traditionally have been very popular in use in parsing. It is essentially a context-free grammar where the production rules have probabilities associated with them. Being context-free grammar, it is more expressive than n-grams. And it also gives us structural relationship. This is hierarchical. And so now we can talk about relations of a noun phrase to a verb phrase and that they compose a sentence or something like that. But then what we don't get here is the relationship between the words because now we're talking about constituency level relations. So it's not quite as good for language modeling, even though it's better for parsing. Kind of as a quick summary, we have language modeling as one task where the primary relation in focus is lexical. And in that case, n-gram is really good for it. But in the second case, we have parsing. In that case, the focus is on structural relations. And PCFG is pretty good for it, but it's not so good for the other task. So one way we want to be able to leverage off of both aspects is to propose a grammar representation that contains both a structural aspect and a lexical aspect. The particular representation that I'm proposing is called Probabilistic Lexicalized Tree Insertion Grammar. It was first proposed by Chavez and Waters in '93, and it is a less expressive version of tree adjoining grammar for people who were interested in tags. In this case, what we do is we represent the rules as tree fragments, and so each tree fragment has some structural component and also a word component. The word gives us, or by combining these trees together, we can talk about how the words relate to each other, but then also the structure tells you something about what the word expects in terms of structure. There are two types of trees here, which roughly correlates to the two types of operations to combine the tree fragments to form a final parse tree. The first operation is called substitution, which works fairly similar to how context-free grammar works. Essentially, we combine two trees based on substituting an entire tree into the leaf node of a different tree with the same label. This typically models some sort of obligatory relations. In this case, the noun phrase is not completed until the determiner has been specified.
Is that what that little arrow in the DT is?
Yeah, so this particular type of tree is called initial tree, by the way, and it has everything else filled up except for the non-terminals with a little arrow saying some other tree should insert into the node. The second operation is called adjunction. It's slightly more complicated. The purpose of adjunction operation is to model modifier relations. So in this case, we can have a tree adjoining into another tree that's already been completed. So in this case, it's going into the interior node in a different tree. And what we are trying to capture here is to have this almost optional modifier to go into the noun node. So what we have to do is to break up the completed tree at that node and then basically insert the entire tree fragment here into where it used to be and then restaple them together. This type of tree is called an auxiliary tree. We can have either a left auxiliary tree which modifies the word from the front or a right auxiliary tree which modifies the word from behind. And actually, there's also constraints on exactly where we can do the adjunction. And this is what gives us the expressive power back in context-free grammar equivalence. So finally, to make this a probabilistic grammar, we associate probability for each possible operation on a node and a set of trees that could adjoin into it or substitute into it. So in this example, we have a right adjunction with a set of 3 trees and also the possibility of no adjunction. And that defines the distribution of what's possible at that node.
It's a little hard to read from back here. What are you conditioning on?
I'm sorry?
What are the distributions conditioned? What are the probabilities conditioned on?
Probably it's a condition on the set of trees, the possible events for at a particular node for a particular operation. So I think, is that your question?
Yeah, it's the tree that's being adjoined into that you're conditionally. Sorry.
It's the possible set of trees that could go into. So in other words, the set of trees that could go into that particular node sums up to 1. That's the distribution.
So basically, if I take all the trees which have some label X star, and sum up the probabilities of their rule, those trees rather.
Right.
So here you have N and N star in all of these.
It's to say that this tree can substitute into that node up there. Oh, actually, I guess I have a point here. So it's defined in terms of this node. That's the condition. It's the distribution defined for that particular node. It's all possible things that could adjoin into that particular node. So in this case, that node's label is n. So
There is a subject one node because you can do nothing.
do nothing is yet another
Do
possible.
nothing is another option.
Yeah.
So there's something less than or equal. So-
Right,
Okay,
exactly.
so this is a generative level, and it's the
Exactly.
tape version of Chavez's probabilistic context. Is that
Right.
Yeah, okay. Good.
Exactly.
It looked like something else in the back there.
So in that sense, there is no conditioning on anything else in the tree. So it's
Right,
in that sense
exactly.
context-free.
Exactly.
That's why it comes out with the same expressive.
So, in summary, I think
Unbelievable.
PLTX has a lot of nice features. One thing I like is its lexical tree representation, so that we can combine both the structural and the lexical aspect in one formalism. Another feature is the adjunction feature, which allow us to relate two words that are very far apart in kind of a long-distance dependency modeling. And moreover, it extends the domain of the property. In other words, if I have a verb and its object is several words down, I can still relate them and then therefore extend the domain of sphere of influence of the VP node with all the sort of stuff that could also modify the object or modify the head verb. And finally, or actually rather second to finally, the insertion constraint keeps the expressive power to be efficient so that we can actually implement this and run it and have some practical applications. And finally, the probabilities allow us to make the training more automated so that we can learn the grammar automatically. Okay. So in the second part of this talk, I'll be talking about how we can induce a PLTIG using an expectation maximization based learning algorithm. And we will also compare it on two tasks with other formalisms. So I got interested in grammar induction because I thought it was a really neat idea that I could just feed the system lots and lots of text and out comes the grammar and it's going to solve all our problems. But then I found out that unsupervised learning is very difficult. So that if you give it just raw text such as Ford Motor Company acquired 5% of the shares in Jaguar PLC and the like, you don't actually end up with a very good grammar. Typically, what gives you better grammar is if you can apply some sort of supervised information to it, such as in this case, we provide the entire parse tree for the sentence. Everything read, however, requires human knowledge, in fact, human linguistic knowledge. And so this sort of learning requires a lot of human effort. And as you'll see later, part of my goal is to reduce the amount of annotation. So one thing I was interested in is to use not a fully supervised learning algorithm, but something more that's both amenable to unsupervised learning and some supervision. And in this case, I'm using a expectation maximization based learning algorithm so that if there is no annotation whatsoever, it could still work. But because it's basically doing a heuristic search to find a local minimum, optimum, that does not need any input from a user, a supervisor. But supervision is still helpful by reducing the amount of unnecessary searches. So if you give it supervision, then the search would be more straightforward. And so what we're trying to do is just to kind of create this sort of middle ground where we could ask people for some supervision, but not necessarily completely be dependent on them. Here's an overview of the algorithm. It's basically an iterative refinement process. So we start off with the grammar in a canonical representation. And then we iteratively try to compute the expected value of seeing the training data given the current model. And then next we try to maximize the parameters to generate the training model, or the training data that we have seen. We continue this until we converge. So the first thing we need to do is figure out a initial grammar. Because EM works as it starts off with an overly generalized model and slowly refine it, we need to begin with something that can generate any string. In terms of TIGs, this pretty much means any word has to be able to modify any other word. And so a canonical form that we propose is something of this format. We have one initial tree, which actually just represents the head of the sentence, so it's an empty tree. And then we have a set of, two sets really, of auxiliary trees representing the word modifying another word from the front and the same word modifying another word from behind. And each tree has uniformly the same sort of pattern where each word can take some modifier from either the left or the right, and you can run a parameter by determining how deep you want the tree to be so that you can specify how many parameters, adjunction parameters you're allowing. So in the E step, we compute the probability that each tree is used in the derivation, which basically breaks down into two parts: the probability that the tree is generating some substring, and the probability that this tree is included in the derivation path. It pretty much is equivalent to the inside-outside algorithm for inducing a context-free grammar, if you've seen that before. And this will give us the expected number of times that this tree has been used in parsing the training sentences. So on the maximization step, we will re-estimate the parameters based on the E step, with the caveat that we need to do some form of smoothing because we don't want to train the grammar to overfit to the training data. So we need a way to deal with cases where, when we haven't seen an adjunction between two trees, not to assign it a zero probability. So we use a deleted interpolation such a smoothing technique, where the probability of a tree adjoining to a node is based on a weighted sum of the true probability of the tree, or not true, but the same probability of the tree adjoining to the node on the training data, and a more general probability of the tree being used in any sort of adjunction at all. Any questions about the formalism before I go on? Yes?
Yeah, how do you define your vocabulary?
How do I define my
Vocabulary.
So this is actually having to do more with the experiment per se, particularly, so I will talk about the experimental setup and then hopefully that'll answer your question. So the formalism I'll compare with is n-grams, where n equals 2 as well as 3, and PCFGs. And the corpus I'm using is the Wall Street Journal corpus. The vocabulary in this case is actually the 48 part-of-speech tag, so I have actually not used the true lexical item of each sentence, but I back off to the part-of-speech tag as my anchor for my elementary trees. So essentially, I look at the set of possible part-of-speech tags, and these are what my anchors are. Does that answer your question?
But in your elementary trees, you have the word there, the word and the tag and another.
Right, so in this particular model, in this particular experiment, the word is the part-of-speech tag. So instead of having the word, imagine that it says NNS, and then it goes up to its internal structure.
And this is true for the n-grams that you're providing with also?
Yes. Yes.
And then you don't have any distinctive non-terminals. All the non-terminals are the same.
Yes.
You get the effect of distinguishing them just from probabilities.
Yes. Right, because also my training sentences are bracketed data, but not, it does not have the label for each constituent as well.
If you do this, then how do you interpret sort of the gold standard? As in, suppose I take a sentence and take its parts done by someone at UPenn, and I crop off all the words. What I'm left with, and would people agree that that's the right parts? Or?
That is a good point. I mean, but I'm currently making the assumption that I'm still taking that as my gold standard. So my gold standard is this tree with all the words cut off and whatever structure it gives me.
Okay, especially because you talk about ambiguities, and
Yeah.
that's going to get like PP attachment.
Yeah.
If you crop off the words,
Well, I mean,
why would I?
yeah, that's true. But in some cases, you might argue that based on the rest of the sentence, you could still perhaps tell. I mean, it's not as good as it could be.
No, I'm not saying it's wrong. I'm just asking you. You must have looked at it. So what's your feeling?
You know, I've actually not done a full analysis of how many true parses there are. I mean, I didn't like ask, you know, I mean, even when I imagined this, I would have to ask a group of people and say, here's a sentence, just look at the part of speech tags, what do you think the structure is? I think that would be a difficult user study to do, so I don't really know what
No, but for example, if you get something which is the wrong part, within 5 seconds, can you come up with a sentence for which it could be the
I see.
right parts? And still
Yeah,
solve those
yeah.
ones?
For Wall Street Journal, though, I guess the sentence would be kind of long, so it might be difficult. Jason.
I'm having a little trouble seeing how you interpret the tree back brackets. When you're, in other words, the brackets assume a notion of continuous constituency, which isn't necessarily present in TIG. So I'm not sure how they constrain the EM algorithm. I guess this question is a little related.
I'm actually not really quite sure what you're asking.
Right. So if the sentence is, what do you think love is? Then the do you think is one constituent, and the what love is another constituent.
Yes.
And I'm not sure how you're interpreting the tree back brackets in constraining the E&M. So this is sort of a question about, it's the standard question when you do a comparative experiment, how you derive anything about the grammar from the data. Right?
Yeah.
And whether the data is appropriately constrained in the grammar.
Yeah. The problem is
Is it a crossing brackets measure?
it's a crossing bracket measure for one thing. I'm trying to answer your first question. I would imagine that none of the formalisms really, well, that's not true. Here. These are for me to use, right? So if you have what, what do you think about blob? So there's sort of, I mean, questions are always a little bit weird. So it doesn't do well. I think these would be cases where you would make mistakes, for one thing. But essentially, I feed it in anyway, just to see what occurs. I'm not sure if this answers your question at all.
Well, maybe we should take it offline, but let me try it one more time.
Okay.
I won't interrupt you. So you're doing something like the Pereira and Chavez partially supervised EMs, right?
Yeah.
And my question is, what parses do you rule out on the basis of tree bank brackets? And is it a kind of crossing brackets measure, which is roughly what they use? I mean, I've answered my own question here, maybe. But.
Yeah. So the answer is, I did not rule anything out. I just put them all in and see whatever happens, and I use crossing bracket as a result of that, as my evaluation.
So you're saying you didn't use the brackets at all to constrain the inside-outside?
Oh, no.
I'm asking when did you throw a parse out of the expectation step for being inconsistent with brackets and not your shot?
Essentially, I took a tree and then whatever the tree gives me as a constituent in contiguous form, I put in the bracket. I did not give it a label, but I put it in the bracket.
derivation versus derived tree. That's what I call it. Thank you.
Ah, okay. Yes, and as you point out, I was always confused. Yeah, so in fact, I do use crossing bracket as my accuracy measurement. There's actually some reasons for that aside from the bracketing issues. It's also because all the trees are induced in a binary branching format, both for the PCFG and for the PLT. So in both cases, the resulting trees would not map to the type of annotation that's given by Wall Street Journal corpus. So that's why we use the part of speech, we use the binary branching measurement. So we ended up using crossing bracket as our metric so that we don't discount extra brackets that we have that would not be in the Wall Street Journal corpus. And as I said, we were looking at two particular tasks, minimizing entropy for language modeling and trying to maximize accuracy for parsing. Okay? Okay, so the result of this was that we find pretty much as we expected. For PLTIG, it did well for language modeling, and it did pretty well for parsing compared to the two formalisms that we're looking at. It didn't quite do as well as trigram did with the language modeling task, where trigram reached a 3.2, this is bits per word, whereas PLTIG had a 3.32. It's roughly in between bigram and trigram, yes. Right, so the bigram trigram actually do not have parses because they're flat. So what I used was a baseline metric of assigning right branching period attaching high. That's why both bigram and trigram have the same parsing score. I put this in there for kind of a baseline sanity check comparison to see, what's the easiest thing we can do that gives us some sort of score. The reason I think why PLTIG did not do quite as well as trigram is because essentially PLTIG is modeling a two-word relations. A two-word can be very far apart, but it's still just two words. Whereas trigram, you have a context of three words, even if they're right next to each other. And other factors that trigram has a lot more parameters than we do, and we have more parameters than bigram does. So maybe that's also another factor. Something that I thought was interesting was that PLTIG has a much better running time, both in terms of number of iteration and in terms of real time compared to PCFG. So for this type of iterative learning, having the lexical representation really helped us. The real time, by the way, is probably very outdated. This was on HP something or other from many, many years back. So now it's probably much faster than 511 hours, but still. Okay, so for the final part of this talk, I want to concentrate on some directives that I'm currently looking at having to do with sample selection, a technique to reduce the amount of human annotation in the training. So, as I have mentioned before, annotation is a labor-intensive problem. We have to, at the very least, in this case, give the bracketing information, if not the constituency labels. So there are various ways we can minimize the amount of annotation. We can try to reduce the amount of brackets in each sentence, or we can try to reduce the number of sentences needed for the training. Today I'm actually going to only talk about the second case, but if you're interested, we can discuss the first case later. So the basic idea of sample selection is that we want to annotate the examples as needed while we train. And we only want to annotate data that's really going to help us, but not anything that comes by. And so to quantify this, you might imagine that each unlabeled training data or potential training data has some sort of a training utility value. And the higher it is means the more likely it's going to help or rather, the more it will help the hypothesis to improve. And what we want to do is to be able to find the set of candidates with the highest training utility values. And we want to apply this sample selection idea to grammar induction. The difficulty, of course, is that we don't actually know what the training utility value is. So we need to kind of do an approximation, essentially computing what we believe to be one sentence to be more likely, or more relatively speaking, bad sentence comfort. We want to be able to pick sentences and rank them so that their relative training utility value would be from high to low, to basically sort them from high to low. So we would always take the most helpful ones first. And to do so, we basically define a heuristic of using the evaluation function to evaluate each candidate for their potential training utility. So the scenario is this: we start with a small set of fully labeled data, and we train on this fully set of data, labeled set of data, as we normally would with whatever learning algorithm. In our case, it would be the EM learning algorithm that we talked about earlier, to get an initial grammar hypothesis. So then we are going to repeatedly, using the current hypothesis and an evaluation function, to evaluate all the possible candidates and then pick the n highest scored ones. And then we'll ask somebody to label these, add them to the training set, and then retrain. And this process repeats until we either run out of data or run out of people to do the data. In this study, I have proposed 3 evaluation functions. Well, really, the first one is a baseline where we just pick random sentences. The second one, we use sentence length as a criteria on the assumption that maybe longer sentences are more complicated and therefore harder to parse, and maybe they'd be better candidates to be labeled. This particular evaluation function has the advantage that it's very easy to compute. And then the third one, we thought maybe we would use tree entropy, using entropy as a way to measure the uncertainty in grammar for the current parses that the grammar generates. So, just to quickly review, entropy, we're measuring the uncertainty. So it's roughly the expected number of bits needed to encode a distribution. So imagine if you have a grammar that gives you something that gives you a lot of parses for one sentence, and they're all roughly the same in terms of likelihood, then you might say that the grammar is very uncertain about the sentence. Whereas if the grammar returns you 1 or 2 parses with very high probability for one of the parts, then you might say that the grammar is very certain about the parse of the sentence. And so we want to use entropy to capture this distribution to tell us how uncertain the grammar is about the sentences that it's generating. So the function is essentially this one here. The top, we just essentially compute the entropy of the distribution of the trees generated by the grammar, and we normalize it by the length of the sentence because we're trying to get to compare it to what happens if it generates all possible trees with exactly the same probability. In a binary tree scenario, you can have on the order of 2 to the length of O number of trees, and so the entropy of that would be length of O. And so essentially we're measuring how far away from how far away is the actual distribution from a totally uniform distribution. So we have conducted 2 experiments in this case. In the first case, we used 360 unlabeled sentences. And in the second case, we used 1,000. And the reason for this difference is because in the first case, so the grammar is still similar to what we've done before with 48 part of speech tags using Wall Street Journal. And we find that roughly 3,600 sentences was enough to train the grammar, but 1,000 was not. And the question here is what happens if we use all the available candidates, and what happens if we have a limited set of candidates. And in the selection phase, we'll pick 100 at each time, and we do 10 sets so that the result you see are averages over 10 sets. And here's the result. This plots the learning curve as we included more training sentences. So on the x-axis is the parsing accuracy on the test. On the y-axis is the number of brackets needed to get that accuracy. Notice that we're using brackets rather than rather than number of sentences, because brackets, I believe, is a better indicator of human effort than number of sentences, because you could have one really long sentence that requires a lot of human effort, or one really short sentence, and you want to consider the long sentences taking more effort than the short one. And so, for instance, on this point, it's saying that in order to get to 80% accuracy, we would need about 15,000 brackets. And using tree entropy as a way to pick out sentences. Whereas if we did it randomly, we would need like 25,000 brackets in the training data. So length turned out to not have really helped at all. We're not helped at all. It's really hard to tell whether this is truly going to, at the very end, whether it really is an improvement or whether it's just some sort of temporary improvement. But tree entropy really does seem to be performing much better. Yes?
Do you know, if you had an oracle that told you what the best 100 trees in each stage
Right.
would be, what would that curve look like?
I do not have that because I'm not quite sure how I would find that.
In a reasonable time, right?
Yeah.
Well, it's clear how you find it, right?
Right, I mean, it's clear how you find it, but you can't, yeah, so I started trying to do that actually, but it was just, has a lot of constraints. Even in my best sort of attempt to finish this sort of curve in a reasonable time, my oracle is actually a really bad oracle. So instead, actually, what I could tell you is, I don't have a graph right now, but I have done this study where I just did tons and tons of random draws. And then I kind of draw a distribution, or not a variance, standard deviation over that and see how the curve fit. And I believe that typically tree entropy, well, the curve would still be within the standard error because it is possible for random to pick this particular sequence as well. But it typically stays on the better half, so it's error on the improvement side. You see what I'm saying? So yeah.
I don't entirely understand the tree entropy. So you take a sentence and then you generate 100 truths for it? Is that
Oh, okay, so let me try that again. I have a grammar, I have a sentence. The sentence is currently not labeled, so it's just some sentence. And I use the grammar to parse the sentence as if it were a test sentence. And then I look at all the possible parses for the sentence. Because it's a probabilistic. So I have like all possible trees for this.
chart.
I'm sorry?
You look at the chart.
Yeah. I mean, so I have something like for a sentence of length L, I could come up with a possible 2 to the L trees, different trees for this one sentence, right? But they would have different probabilities. So that defines the distribution. And that's what I'm characterizing what we're using.
So you don't actually generate the tree, and you given a distribution that's represented in the chart?
No, I do generate the trees, right? I mean,
So you generate, how
I
many trees do you typically generate?
all of them, right? Using the chart method. So, okay, I
It
see.
doesn't have to enumerate, it doesn't take exponential time to enumerate.
Right.
That is the point that we're talking about.
Yes.
Right. So, in fact,
You can get the entropy of the chart.
yeah. Yeah.
Just by dynamic programming.
Yeah.
Yeah, exactly. It's a slightly different dynamic programming than, or it's a different number that you're computing, but it's the same technique, using a table and building it up as you go along.
So my second question is, does something magic happen between 70 and 80? It looks like an idea of a curve, and
Yeah, I don't know. I'm even wondering maybe something magic happened rather than 78 and 80, but rather between 10,000 and 15,000 brackets. That seems to be where it curved off. At some level, I think there is kind of the expected performance of this system. And the system with this particular training framework, I think, has a performance level of about 82%. And that's why, no matter what, it's going to curve off, tail off. So I guess what it really says is that the biggest improvement is over the yield to curve in that particular training instance. Oh, I should also point out that each point here plotted is actually, I only plotted points that are significantly better than the previous point, so that you're not seeing every single point. So in other words, these differences are actually at least statistically significant. I mean, whether they're truly significant, whether you care even 1% performance of parsing, that's up to the application, of course.
You mentioned that on the blue curve,
Yeah.
that you had many randomly drawn samples.
Mm-hmm.
So if you could put a band with, let's say, one standard deviation, I don't know what that would be. How thick would that band be?
It would be thick. I mean, it depends on how many you draw. So I wish I brought the plot, but I didn't. But it would be wide enough to include everything, I think. Right? Because I mean, if you do enough of them, right, it's going to be wide. So
There are some which are even better than the tree entropy.
oh, I'm sure.
And
It would not surprise me at all.
One candidate actually is the active learning stuff that Bryce and I used in our thesis.
I'm sorry?
One possibility actually is the active learning stuff based on
Comedy?
Bootstrap,
Yeah.
where you take lots of samples of trees and you see the extent to which they disagree on parsers.
Yeah, exactly. Possible future work. Yeah. Let me just quickly describe the smaller set, which I think you basically see the same trend, but I thought there's this one little bit that was interesting, so I want to point it out. In this case, after having seen all of them, after having seen all 1,000 sentences, tree entropy actually gives you a slight parsing increase in terms of accuracy at the end, rather than converge to the same point. And this is because I'm essentially changing the order in which the example is being seen, so that it's in a way going on a different search path. And for some reason which I'm not 100% understanding, it finds a better local minimum than random, which I thought was promising, because if we have a data sparsity problem, this is actually a way to possibly counter that.
Wait, are your models retrained at each step?
I'm sorry?
Do you retrain everything at each step, or you just adjust weights?
Retrain everything? No. What do you mean? I want to be more specific about answering your question.
Well, I see no reason for it to be different if you're actually retraining with all the sentences, unless you just adjust them.
No, you do retrain all the sentences. So the first time you see 100 sentences, and the second time you would see 200 sentences. But it would be between the two different evaluation functions, they would select different sets of sentences. So
Right, but when you have the same set,
iterations.
I mean, the plot included all the possible brackets you have, all your training size. Because if you have the entire training size, it doesn't matter if you choose randomly to take
but in this case, so if it's a history-based learning, then it doesn't. You should end up in the same point at the end. If you have seen all of them, you should end up at the same point. In this case, it's actually somewhat different because what you're seeing is, this is actually one hypothesis I had on why it does better, that you're seeing some of the harder sentences more times. So for this one sentence that you don't understand, you're actually seeing it 10 times instead of 1 time.
I see, so you're actually drawing with replacement.
Well, it's actually without replacement, but you could imagine it. Right? The first time I pick, let's say, sentence 1 through 10, and the second time I pick 10 to 20, but it's concatenated, so it's now 1 through 20. So 1 through 10 I've seen more times because it's iterative.
You've trained on it 4 times.
Yeah.
And you don't reinitialize the algorithm when you start with the 20, right?
I'm sorry?
So you converge somewhere with 10.
Yeah.
You start there when you
Yeah,
have the next
exactly.
10.
What's the initialization?
I guess that was my initial question.
Ah, okay. I heard some other questions. No, okay. Okay? Okay, so in conclusion, I covered a whole bunch of stuff that I've been looking at recently. In terms of grammar representation, I was working on using PLTIGs to combine the best features of n-grams and PCFGs. And then I created a learning algorithm for it so that we can use partial supervision to train up the grammar. And finally, we looked at ways to make the training process more efficient in terms of human annotation time. And we showed that uncertainty is a possible way to approximate training utility value of unlabeled data and use that as a metric to pick new sentences to be labeled by human. So some things I'm still thinking about in terms of PLT. I would like to cast it in terms of what I'm currently working on with folks at Maryland on machine translation issues, possibly using some sort of synchronized PLT so that I can do some sort of modeling of simultaneously have modeling dependencies on 2 different languages at the same time. And then I'm still interested in applying annotation, minimizing annotation in training data techniques to other parsing techniques. Currently looking at doing similar work using Collins' parser. Also interested in finding other evaluation methods, possibly using a committee-based approach. And also interested in applying it to other natural language processing tasks. All right, thank you. Questions? Yeah.
So how well do you think it would work if you took humans out of the loop entirely?
How well do you think? What do you mean? I mean, so the problem was if you meant completely unsupervised, then you wouldn't be sample selecting, right?
Well, I don't know, you could still look at the entropy, couldn't you?
But, oh, I see. But you would just, well, when would you?
Take the maximum likelihood bars, so you take the ones that have low entropy,
And then?
train.
I think what Bill's suggesting is a kind of confidence-based, where, so if you think about something like David Jurowski's work or other co-training stuff, or Hindle and Ruth, I guess, would be the...
I see.
It would be the kind of reference. Marty Burst, I think, did that kind of thing even earlier, but where you add to your EM pool based on things that are...
I see.
Based on the things that you can parse with reasonable accuracy instead of drowning the thing to start with and see if half-baked interpretations.
I see. That would be an interesting thing to try, but I haven't tried it. I don't know how that would work. I mean, I sort of imagine it still wouldn't work quite as well as any sort of, even a little bit of supervised training data. I mean, just because every attempt in unsupervised learning has been so full of sad stories. But it doesn't mean that we shouldn't, keep on trying. So it might or might not help. I don't know. Yeah.
I have a question about the active learning part. what relation do you think there is between what you're looking for, the tree, I'm sorry, the training utility value of a sentence and tree entropy? I mean, clearly, harder sentences might have something to learn, but there can also be junk.
Yeah, so that is, as I say, a heuristic, right? I mean, you might even say, well, typically, longer sentences have higher tree entropy as well. So it was a way for me to characterize uncertainty. But uncertainty is not the only way to do sample selection. You can use confidence, how confident you are, which is actually different from how uncertain you are. Confidence, you can say how many times you have seen something versus how many times you haven't seen something. If you haven't seen something, you've only seen it a couple times, you might be very unconfident about it. But if you've seen something many times and you've decided that you don't know what to say about it, then you're very confident that you don't know anything about it, and more data is not going to help you. So confidence is yet another way of looking at the sample selection problem. Or you can even look at an error-driven situation where you say, you parse something and then you say, how often have I made mistakes on previous attempts? And then I might want to search for data that look more like things that I've previously made mistakes on. So there are actually many different things to try, and entropy was just one of them. And I tried it, it actually worked out pretty well. But I'm sure there are many, many other interesting ways of characterizing this.
And how would you go about searching trees that look like the ones you did made error on?
So that's an interesting question, and that's what I'm currently trying to think about. Trying to see whether it would be helpful to look for sentences with similar types of words, but that might not capture what's really missing, which was kind of the internal structure. I mean, it might be entirely different sets of words, but somehow they have the same internal structure. Because I don't know that in the first place, it would be hard to figure out what they are. But I might also look at sort of part of speech tags maybe as another way of backing off. But these are definitely issues. You look.
I thought you were using parse.
Oh no. So now that I'm working with a Collins parser, it's actually real words. So then I can look at part of speech tags.
And how close do you think this would be from what Grace did? A combination of classifiers. How much the diversity of classifiers would give you the utility of a sample?
So what this situation is, the difficulty of this is that it's a very hard classifier. I mean, you can see parsing as a classification if you like. There's one parse that you want out of an exponentially many number of parse trees. Right? So that's in a way a classifying. I'm saying out of all these possible parse trees, I want this one. So in that sense, it's a very difficult problem. I mean, you can look at it in terms of preposition attachment, which is much easier, where you have just two classes. I mean, especially in the simple preposition attachment case, where you look at noun attached versus verb attached. It's a one-bit decision. In this case, it's much harder.
Well, the measure wouldn't be vote entropy. It would be something like caliburgence among the distributions of parses produced by the different bootstraps.
Okay.
I mean, you're right that we've got too many parses for vote entropy to seem reasonable. But if you don't only look at the top parse, if you don't only look at the majority classification, you might be able to come up with some really measure.
Yeah, that would definitely be a possibility. I mean, I would only be able to tell you after I've done something.
So a lot of modern CFG parsers include a lot of information which extends beyond the domain of locality on the rule. So when you look at the grandparent head or the sibling. So have you thought of ways to or played around with including any kind of that information?
No, not yet. Not yet.
That'll work. What do you say?